So in terms of optimization with multivariable, I'm choosing a very simple example at first where we will identify the critical values after taking the first order derivative and setting it equal to 0, and then through the second order operations, that means by identifying a Hessian matrix and by forming a Hessian matrix, then identifying the determinant, we will take decision whether the function is at its relative maximum or minimum. So here I'll be following the simple procedure in order to solve for this system of equations and to identify the critical values. Let's start. So this is an example where the given function is z is equal to 2x1 square plus x1 x2 plus 4x2 square plus x1 into x3 plus x3 square plus 2. So given this equation, at first we need to identify z of x1, which is will be differentiating the given function of z with respect to x1 first only. So it will provide us with 4x1 plus x2 plus x3. I hope by now you all are an expert of differentiation, as you have practiced it enough in the previous concepts. So I'm not stretching on this part. How did we get the zx1, the first order derivatives? You should be able to solve it by yourself by now. So now let's look at zx2. So here now I'm differentiating the given equation z with respect to x2, where I get x1 plus 8x2, set it equal to 0. This is my equation number 2. And then finally, if I differentiate it with respect to x3, then I get zx3 is equal to x1 plus 2x3. Then I set it equal to 0. So these are the three equations. Now, let's say from equation number 2, what can I write? Let's see again. So equation number 2 provides me with x1 plus 8x2 is equal to 0, or we can write 8x2 is equal to negative x1, or x2 is equal to negative x1 by 8. Let's say this is equation number 4. Similarly, from equation number 3, we can write 2x3 is equal to negative x1, or x3 is equal to negative x1 by 2. My bad. Let me write it again. So negative x1 by 2. And let's say this is our equation number 5. This is our equation number 5. So what I have done basically, if you can see, I have tried to form an equation for x2 and then in terms of x3. Definitely, I would like to plug in this x2 and x3 in one of the equations so that I can at least solve for x1. So now if I plug in all these values in equation number 1, what do I get? So zx1 was equal to 4x1 plus x2 plus x3, which was equal to 0. Now instead of x1 x2 and x3. x1 for x1 remains same. Instead of x2 and x3, I can write a negative x1 by 8 from equation 4, and from equation 5 I can write negative x1 by 2. Hopefully you have understood it. Okay, now if I do the LCM, I get 8 over here. Here I get 32x1 minus, I get x1 over here. Yes, I get x1 over here, and then I get a negative 4x1, and then set it equal to 0. So if I cross multiply, 8 into 0 becomes 0. I'm simply left with positive 32x1 minus a negative 5x1, which is equal to 0. Or in other words, it is basically 27x1 is equal to 0. So in that case, x1 is equal to 0 by 27, which is equal to 0. So the critical value for x1 is 0. If x1 is 0, then plugging this value in equation 2. If x1, again let me write, if x1 is equal to 0, I'm plugging in this value in, suppose, okay, let's say in equation 4. So then what do I get? I get x2 is equal to 0 by 8, which is equal to 0. And again, if x1 is equal to 0 and I plug in this value in equation number 5, in equation number 5, then what do I get? In equation number 5, I get that x3 is equal to negative and then 0 by 2, which is altogether 0. So we get that all the values x1, x2, and x3 are providing us with 0 values actually. So these are the critical values that we have solved for. So this is just simply by following our regular way of solving the linear system of equations. Anyways, later on in the next example, we will see that how we can apply a Cramer's rule to solve for these critical values. Now let's move towards the second order condition. Now, if you remember the first order derivatives, they are simply zx1 is equal to 4x1 plus x2 plus x3. I'm writing it again to make you remember what were the first order partial derivatives. Then there was zx2, which was equal to x1 plus 8x2. And then there was zx3, which was x1 plus 2x3. Now this will help us to form the Hessian matrix, as there are 3 variables. So it will be a 3 by 3 matrix with a column for x1, then a column for x2, and then a column for x3. And where from I'm getting this value? Just simply from here, 4, right? Oops, sorry. Yes, just simply from here, and then we know that here a 1 is multiplied, here also a 1 is multiplied, so we get 411. Then from here we get a we get, I don't know what is happening. Let me see first. Okay, undo, and then I press draw. Okay. Something is happening that I don't know. Just give me some time. Is there something automatic that I have pressed? I don't know. Just give me some time. I'm sorry for this. Let's clear this one and let's write again. Okay, so if let's see. Okay, so I say that zx1 was equal to, okay, I think I will just form the Hessian matrix now. I'm really sorry for this time loss. Okay, I'll form the Hessian matrix. I think you have by now understood how to form the Hessian. So from the first order derivative, then I get H is equal to 4, 1, 1. Then from the next one, I get 1, 8, 0. And from the third one, I get 1, 0, and 2. Now here, if I say H1 is equal to F11, determinant of F11, this is nothing but the first principal, leading principal minor, which is 4. So we write 4 over here and we see that this is greater than 0. Then for the next one, we will be taking this, the 2 by 2 thing over here, okay, which is consisted of, so H2 is consisted of, as I said before, F11, F12, F21, and F22. So here is your matrix formed. Now you plug in the values in terms of a 2 by 2 case. So you get 4, 1, 1, and 8. By now you have learned how to identify the determinant. So I'm keeping the calculation short. This is 32 minus 1, which will become 31, and this is also greater than 0. So basically we have multiplied the principal minor and then subtracted the off principal minor value from it and got that H2 is also greater than 0. Now it's our turn to calculate for H3. Let's do that. Let's first erase this part and then we will solve for H3. And let's see whether that value is also greater than 0 or not. Okay, so in terms of H3, then you know how to identify a determinant. This will simply be, let's say, H3 you are trying to identify the determinant is equal to 4, 8, 0, 0, 2 minus 1, 1, 0, 1, 2. I'm going to the next line, plus 1 into 1, 8, 1, 0. So basically, while we are trying to identify the determinant, what are we doing? the first column and the first row we are omitting. We are omitting the first column and the first row. That's how we are left with 8, 0, 0, 2. This is the first one, right? That's how we do the rest. Now, after doing the calculation, what do we get? We get 4 into 16 minus 0 minus 1 into 2 minus 0 plus 1 into 0 minus 8. Again, I can understand. I hope that you understand this calculations well, why there is a negative sign, why there is a positive sign, as you have learned it in matrix operations part thoroughly. So I'm not going into details. From here we get 64 minus 2 minus 8, which is providing us with a value 54, which is again greater than 0. So thankfully we have got H1, which is greater than 0, H2, the determinant, which is also greater than 0, and H3 is also greater than 0. As a result, we can say that the function is at its relative maximum. And that's how a multivariable case is solved, by using a Bayesian matrix. I will show you another example where we will be using the Cramer's rule method to solve for the critical values now. So please watch the next video to go through this particular operation. Thank you.